Okay, in the lecture about classification, we mentioned the confusion matrix, including the four important values for evaluating the performance of a classifier: the true positive, the true negative, and the false positive, and the false negative. Based on these four values, we can define three important metrics called precision, recall, and accuracy. These all measure the success rate or error rate of a performance of a classifier. And we also defined a balanced metric which integrates precision and recall, called F1 measure. Now let's extend the metrics from error rate to cost-sensitive cases. Each decision made may have a cost, say in the cancer versus healthy diagnosis by doctors. Healthy persons may be misclassified as having cancer. This is false positive. False positive introduces a cost, as the person misdiagnosed needs to take some unnecessary therapy, which is miserable and expensive. But the cost of misdiagnosing patients with cancer as being healthy is much higher, because this may cause a loss of life, right? So false negative has a higher cost. Then what is the total cost of our doctors in making mistakes? We cannot simply look at the error rate. The total cost made by a doctor is dependent on how good the doctor is. That is to say, it depends on the probability of a doctor making false negative mistakes, and similarly also depends on the probability of a doctor making false positive mistakes. Then the overall cost also depends on how many people can have cancer in a certain geometric area. So we will multiply the cost of making false negative mistakes by the probability, the prior probability of encountering persons with cancer, further times the probability of these patients with cancer being misdiagnosed. And similarly, we will multiply the cost of making false positive mistakes by the prior probability of seeing patients without cancer or healthy persons, which is further multiplied by the probability of these healthy persons being misdiagnosed as having cancer. If we do some transformation of the equation, let's denote C minus given plus, which is the cost of misclassifying a positive sample to negative, and denote pi of plus as the prior probability of positive samples. Now we combine the first two terms in this equation, or in the multiplication, to alpha. And similarly, the cost of a misclassifying a negative sample to positive times the prior probability of seeing negative samples. And we rephrase this part, the first two items, to beta. Now alpha and beta are dependent on the problem. In this case, the total cost is a linear function of these two probabilities. The first probability is the probability of making false negative mistakes, and the second probability is the probability of making false positive mistakes. And these two probabilities are dependent on the model. Now we can have the equation like this. as in the last slide, then because this probability is equal to 1 minus the probability of making true positive predictions. So we can replace the probability of making false negative mistakes with 1 minus p of plus given plus. If we replace this probability with the 1 minus p plus given plus, then the total cost equation becomes this. And now we can see it is a linear function of the probability of making true positive predictions, which is the true positive rate, and the probability of making false positive predictions, which is the false positive rate. In practice, we may not know precise values for the costs of making misclassifications and the prior probabilities. Thus, we do not know the precise values for alpha and beta. But even though we do not know the precise values for alpha and beta, we can still determine a subset of the classifiers that cannot possibly yield the lowest cost, whatever the values of these, or whatever the value of the cost of making misclassifications and the prior probabilities are. And this is done by doing the so-called ROC analysis. In ROC analysis, each classifier is characterized by two performance metrics, as this equation shows. The first performance metric, as we said, is the probability of making true positive predictions, or the true positive rate. It is desirable to have a high true positive rate. But this is not enough. Think about the fact that the percentage of persons who get cancer is much lower than those without cancer. So this is the reality. So less people have cancer and more people do not have cancer. Based on this assumption, if we have a doctor and the doctor treats every person coming to the hospital as having cancer, this makes a 100% true positive rate, but it is not useful at all because too many healthy persons are misdiagnosed, resulting in huge cost. So this means even though we have 1 for p plus given plus, which minimizes this term, but p plus given minus is also very high, so which still results in a large total cost. So in this case, we need a second performance metric, which is the false positive rate. We want all healthy persons to be correctly diagnosed as healthy. In other words, we want the rate of misdiagnosing healthy persons as low as possible. So the ideal classifier should have a high true positive rate. So, for example, the true positive rate of 1, and a very low false positive rate, say 0. So this is our ideal. Unfortunately, almost no classifier can reach this ideal because a classifier will always make some mistakes and will always be somewhere between the ideal and the worst, which misclassifies every case. So in this case, we can represent as I just said, a classifier as a two-dimensional point specified by the true positive rate and the false positive rate. Now, representing all the classifiers in a diagram in the two-dimensional space, we can see that, okay, the ideal is the left top corner, this point, which has the true positive rate equals to 1 and the false positive rate equals to 0. And the worst case is the right bottom, which misclassifies all the positive and the negative samples. So our ideal is to find the best classifier that outperforms all other classifiers in both aspects. However, this cannot be guaranteed. What can be guaranteed is we can exclude those who cannot perform better than others. These are called the suboptimal classifiers. For example, if we look at this green triangle, its TP rate is worse than the point above it, and its FP rate is worse than the point to its left. So this green classifier is suboptimal, should be excluded. We should not choose this classifier for our end task. Then let's look at this one, this green inverted triangle. How about this one? It is better than the left black point in true positive rate, but it is worse than the left black point in FP rate. And similarly, compared to the right black point, it is better than the right black point in FP rate, but worse than the right black point in TP rate. So this means this green inverted triangle is not superior to other classifiers in both dimensions. So possibly this is also a suboptimal classifier. Now the question is how to determine it is suboptimal and exclude it. This is based on a concept called the convex hull of the points connected by these red dashed lines. Below the convex hull, we know the classifiers are suboptimal. But this is not to say that the classifiers sitting on the convex hull are optimal. Instead, we can only say that there cannot be any other classifier which is better than the classifiers on the convex hull in both performance metrics. So if in this case, or in this sense, if we have a classifier which is below the convex hull, then this classifier is a suboptimal classifier, and we should not choose this suboptimal classifier for our end task. Now the blue dotted line from the left bottom up to the right top is the no discrimination line, from which we cannot say the classifier is a useful classifier. Instead, it behaves like a random predictor. Now finally, a few words about the no-free lunch theory. So suppose we are interested in the generalization performance of a machine learning algorithm, method, or model. And suppose we have no prior preference for any kind of model about the target. So can we say method 1 is always better than method 2 in any domain. For example, can we say neural networks are always better than decision trees in any application domains? So this might seem true to us because these days neural networks and deep learning is quite hot and quite successful and achieves the state of the art in almost all domains. And also decision tree seems to be a quite old-fashioned algorithm. But unfortunately, this statement is not true. And in fact, there is a very famous AI researcher in a Chinese university, Nanjing University, who is the chairman of the Association for the Advancements in Artificial Intelligence, who had developed a very decent new algorithm for decision trees called deep decision trees, which performed at least as well as many deep learning methods. So this is a justification for this statement that we can't say one machine learning algorithm is always better than another machine learning algorithm in any application domain. So this is called the no free lunch theory, which says there is no universally best model. And the reason for this is that a set of assumptions that works well in one domain may work poorly in another domain. Now, a few more explanations or comments about the no free lunch theory. So, no free lunch theory says a general purpose universal optimization strategy is theoretically impossible. So, in practice, we should utilize prior domain knowledge as much as possible and customize the optimization pipeline or routines for the specific application domain. So as a consequence of the no free lunch theorem, we need to develop many different types of models to cover the wide variety of data domains and application domains in the real world. And for each model, there may be many different algorithms that we can use to train the model, which make different trade-offs between various performance considerations. Now, this is also the reason we have this module, because there are different machine learning algorithms and models to learn and to use in practice. We have a wide range of choices, and we can't say a machine learning model can be used as the best model in any application domain. So we have to try out different machine learning models and choose the best one, possibly. And note that we have two usages of the word model here. So the word model can be a specific configuration of a machine learning algorithm, a method with the parameters optimized. So this is something that is learned, determined by the learning stage. This is the narrow sense of the model. Also, a model can also be used to denote a specific category of machine learning methods that we can choose and apply to solve a machine learning problem. So this is the more general sense of model. And this also appears quite frequently in machine learning theory literature. In machine learning papers, typically the authors will say that we develop a novel model, and in this sense, the model means a specific category or specific type of machine learning method. As a summary, no free lunch theory says any statement of the form method 1 is better than method 2 really means that method 1 is better than method 2 for this specific problem or this specific class of problems. The example is we can't say surgeon is a better doctor than physician, right? A surgeon is a better doctor only in surgery, but a physician is a better doctor in internal medicine.